So thanks everyone for joining. My name is Dan Gottlieb. I run a small consulting firm focused on FHIR, and I'm excited to talk about kind of a new project called Flat Quack. But before we get started, I wanted to step back a little bit and talk about kind of the goals of this project and where it came from. I worked on my first clinical data warehouse back in 2010. And things were a little different back then. We didn't have FHIR as a standard. Most clinical data warehouses, or most data warehouses in healthcare, were really based around claims data. And the few that were based around clinical data were generally not very performant. So my team ended up kind of building our own schema for clinical data. And that worked okay, but kind of over time, we had to maintain that schema. And so we had a lot of responsibilities with coordinating with multiple sites to upgrade the schema as they needed to look at new types of data. Fast forward to 2019, I worked on a research project with the National Institute of Health here in the United States to develop a data warehouse for a research project. And in that case, we had two big things that had changed from 2010. The first thing was that FHIR existed. So instead of having to develop a clinical schema from scratch, we could kind of take these hundreds of thousands of expert hours that had gone into FHIR and just use that as our base schema. And then the second thing is that databases had gotten a lot better at working with hierarchical nested data. Ryan and Arjun talked a little bit this morning about kind of why healthcare data sort of fits well in that format, but kind of some of the difficulties of working with it. And the fact that databases could take that data now and flatten it meant that it was just easier to use FHIR it was reasonably easy and possible to use FHIR as a base schema. And so we built that data warehouse on top of Google BigQuery. A couple of years later, I was working with another team on a different clinical data warehouse for a federated research system. And we wanted to use a lot of the ideas from that initial work. But since we were building on AWS on top of Amazon's Athena database, we weren't able to directly use the existing work we had done on queries to flatten data and queries to work with that flattened data, and that all had to be rewritten, which is why it was so great to be able to work with all the folks on the call, all the presenters on the call here, and a number of other folks in the FHIR community over the last couple of years on developing the SQL and FHIR specification so that those queries can be portable between databases and also simpler to write. And so my particular interest here is kind of working with medium-sized data. So we have some large data in healthcare, we have some small data in healthcare, but there's also a lot of use cases where you have a fairly large data set, but not a huge data set. So things where you might want to be working on a data set that's extracted from a clinical system for a specific research project. Or you might want to be working with a cohort from within a much larger organization. So maybe all diabetic patients within a healthcare organization. So you might have, a couple hundred gigabytes of data, maybe a few million FHIR resources, 100 million FHIR resources, but not billions and billions of resources. And for that size of data, it turns out that the DuckDB database, which is getting a lot of momentum in the analytics space, is designed exactly for those use cases. So in this project, I wanted to try to see how we could apply SQL and FHIR definitions in combination with DuckDB to work on data for these kind of medium-sized data use cases. So the project's called Flat Quack. It was named by ChatGPT. I told it to come up with some names around flattening FHIR and DuckDB, and that's what it came up with. So if anybody has a better name, happy to consider it. Actually, I'd love to consider it, but that's the current name. So let's dig in a little bit. I want to start by talking about DuckDB since it's fairly new and folks may not be familiar. The picture on the upper side of my screen there, upper right of the screen, is Mo Huijsen, who's the creator of DuckDB. He's a professor in the Netherlands, a computer science professor, and that's his pet duck on his shoulder, which is how DuckDB got named. I don't think the duck wrote any code, but sounds like it was an inspiration to develop a high performance database. So a couple things about DuckDB. It's open source, freely available. It was designed from the ground up to be very fast. It's an in-process analytic engine, so you don't set up a separate database server. It just kind of runs within whatever software process is doing the analytics. So it's been embedded into a lot of data analytic engines, including commercial engines. And so it actually just hit version 1.0. And so they've kind of promised backward compatibility in a lot of ways going forward, as well as commercial support. So they set up a kind of a private organization that does commercial support for the database to help support some of these commercial use cases. So I guess the reason I bring that up is really just that I don't like to use software that looks like it might go away soon. And DuckDB looks like it has momentum and it has a fair bit of support. One of the things that I think is really great about DuckDB is that there's native high performance kind of often custom written interfaces to a lot of different data formats. So you can start with ND-JSON files or Parquet files or CSV files, and they've written readers for those from scratch that are multi-threaded and high performance, work really well on a multi-core processor, dividing up the work. And they can even do things like query for wildcard files. So you can say, find all ND-JSON files in this directory and treat them as one imported table. So it's really great for kind of working with data in different formats. DuckDB can actually connect directly into other database systems and read their data without having to go through kind of an interface into those systems, and can push down some parts of queries into those systems so that I can pull data a little faster. So if you have some FHIR data in Postgres, or if you want to output the results of your flattening into Postgres, you can do that. Obviously, it won't be as performant as kind of working in Postgres directly, but it's a capability that DuckDB can kind of throw on the pile for some use cases. And then they've been working really hard on improving data lake support. So it has great support for Apache Iceberg and some support for Delta Lake. I think they're working on kind of improved support. So both of those are plugins to DuckDB that can kind of natively read those formats, and it can actually read over the network. So if you have a bucket of ND-JSON on S3 or a bucket of Parquet files or a bunch of Parquet files in Delta Lake format, you can read those directly from DuckDB without having to kind of first retrieve them and pull them down. And that has some performance implications because DuckDB can be smart about which files it reads and which files it doesn't by just looking at the indexes in the files or your directory structure. So lots of ways to get data in and out of DuckDB, which is really cool. And then DuckDB turns out to be really good for FHIR for a couple reasons. One is it has strong nested data support. So it has native types for structs and for lists. And so those are really fast to work with inside the database. And as we've discussed several times, FHIR kind of has a lot of nested repeating values. And so that's a good fit from that perspective. And also, as I mentioned, has a parser for ND-JSON that's really fast. And ND-JSON is the format currently that most electronic health record systems export when they export bulk FHIR data. So you can kind of take the raw export from an EHR, from an electronic health record system, and pipe it into your flattening tools without having to do any data transformation or even kind of merge the files ahead of doing that. And we'll look at some in a demo. And then lastly, there's a bunch of SQL features that make DuckDB really good for working with clinical data. One of the things I like is you can do fuzzy temporal joins. So you can join two tables on dates, even if the dates don't exactly align. So if you wanted to find a lab result that was very close to a procedure, and they both have dates, but they don't have any identifiers in common, you can actually join those tables fuzzily on the dates, and it'll find the nearest lab result of a particular kind to a procedure and join those into a single table. You can also do things like find the most recent values for a user or for a patient in this case in a highly performant way that's a little faster than window functions. But that's kind of a performance optimization. But there's a lot of good SQL stuff in DuckDB that works well for healthcare data. I was excited to try out some of this. So I built a tool called Flat Quack on top of DuckDB, or generating specifically SQL that works very well with DuckDB. And this is a brand new tool. So it's a software. I actually released it on Monday. So it's very alpha software. And we're going to do a live demo. So that'll be interesting. But I wanted to talk a little bit about kind of some of the structure inside the software. So FlatQuack is a SQL compiler. Nikolai is going to talk a little bit about different types of view runners, different ways you can use SQL on FHIR view definitions. In this case, we're actually DuckDB compiling the SQL into, these view definitions into SQL files. And then you can take those SQL files and use whatever tooling you want to work with them. So there, you can actually run them within the FlatQuack command line. You could run them within a DuckDB command line interface, which has some nice features like progress bars. You can integrate them into an existing workflow tool like Apache Airflow, a SQL orchestration tool. You can integrate them into a DBT or a SQL transformation tool like that because it's just SQL. So it can kind of fit into your existing pipelines, into your existing infrastructure. And so that turns out to be pretty useful in a lot of use cases. Other use cases, you might want a more integrated solution. Let's see. So sorry, I got a little off track. Somebody's texting me heavily while I'm presenting. Yeah, the other kind of neat thing about the FlatQuack architecture is it comes with a bunch of built-in SQL templates, and you can kind of choose a template that impacts how your SQL is transformed. So I have some built-in templates for example, pulling in ND-JSON and generating Parquet, which we'll use in the demo. I also have an example template for generating out of your SQL on FHIR View Definition that can then flow into a DBT transformation where you would combine multiple tables and create some derived models. You can also create your own templates. So if you have a particular naming convention in your files, or if you want FlatQuack to create tables in Postgres with a certain names or a certain structure, you can kind of customize that to some extent by passing in a template in addition to your SQL and FHIR View definition, and the output SQL will reflect that. And then you can, as I said, you can kind of run this through a DuckDB engine. There's a built-in one, but you can also use kind of any DuckDB engine. In the demo, we're going to pull in some bulk FHIR and NDJSON as if you got it out of an EHR. And then we're going to flatten it into tables in Parquet. Of course, you could also put it into, for example, a SQLite database or a Postgres database or other formats, and then access it from a BI tool or something like that. We'll actually just take it into Excel and take a look at it. So for a demo, I wanted to come up with a fairly common real world use case. And so where I landed was a real common thing to do is to take your healthcare data and create a care management work list. So in this instance, you might have some risk management or some shared risk of your patients with a payer, or you might be an HMO, a healthcare organization that's more universal. And so in addition to kind of treating patients as they come in, you might want to monitor patients' health conditions and have somebody reach out to them if they're high risk. And that's often done by creating these care management work lists, and then you have a care manager kind of call the patients. And so in this example, what we're going to do is create a work list of patients who have uncontrolled diabetes and have their home phone number and name so that I'm able to pull contact information for the patients. We want to be able to find patients who have a recent or who have an A1C lab and look at whether their most recent lab was elevated. This is a little bit simplified from a real world use case. We're starting assuming that a cohort of diabetic patients has been exported. You could also look for patients who have a problemless condition of diabetes. Another thing you might want to do in the real world is look for patients who've already had a recent office visit so that you know that they're active patients. You might also want to prioritize patients who have other conditions like hypertension and put those at the top of your work list. You might want to ignore patients who have an upcoming appointment already scheduled because you wouldn't need to reach out to them because they're coming into the office. So there's like a bunch of additional types of view definitions you might want to join into some of these SQL queries. I simplified it a little bit, so we're just going to look at the patient contact information and the patient lab results. So starting with the lab results, on the left here, I've put a FHIR observation that's a lab result. This is a lab result for hemoglobin A1C, which is the value we want to track. If it's elevated, it could be someone with diabetes could be at higher risk for complications. So that's the lab result we're interested in. But we only want, and this is somewhat simplified, I actually cut out a lot of fields from here. And of course, in a data set, you'll also have other labs as well. So we'll need to think about that. And all I really want to pull out of this is the patient ID, the timestamp of the lab, and the value of the lab. So there's like a lot of extraneous hierarchical information here that I don't need. So like I said, we want to pull these three values. You can see where they are in the source observation. And then we also want to do a little filtering. We want to filter to just the lab we care about for this use case, and we want to filter to only labs that are completed, so they have a status of final or amended. I think I look at both. And so here's a simple view definition that does this, both this filtering and pulls out these fields. And so this is going to be the view definition that we're going to run on our sample data set as part of the demo. I also mentioned we want to grab the patient's home phone number. And this is a little bit more tricky in terms of kind of hierarchical and repeating data. So you'll notice this patient has a maiden name and an official name, and we just want to extract that official name. They might also have multiple first names or first and a middle name, and we want to kind of combine those because we don't care about splitting up the name into family name, given name. We just want to know what to call the patient when we speak to them. In the telecom group there, in the telecom element there, you can see we have a home phone number. We might also have work phone numbers. We have an email address, so we want to be able to filter to just phone and just phone number that's designated as the home number. We might even want to have fallbacks where we fall back to a work number if there's no home number there. So this is a case where we want to pull out some simplified data. There's a lot of data in the patient resource, a lot of demographic data, and then a lot of the name data and telecom data. And so we want to use a view definition here. This is a great example of a view definition to actually just filter for home phone and to combine the name into the name we actually want to call the patient. Have two flattened tables coming out of this view definition. So we'll have the patient, we'll have their lab result and the dates of their lab result. We'll actually have multiple lab results for each patient potentially. And then we'll have one line with their contact information. And so at this point, these are tables that a lot of SQL tools, as Ryan mentioned, are really good at working with. So we could pull this data into, for example, Salesforce, which a lot of organizations use to manage care management outreach, or we could pull it into a visualization tool like Tableau and kind of auto-generate some join SQL there to be able to kind of create a common table. Because what we really want to do is get out this work list of just the patient ID and their last lab value if it's elevated. And we want to filter out the patients who don't have elevated labs. In this case, I just wrote some SQL. As you can see, it's like fairly straightforward SQL. I did put in, I couldn't resist. I put in a little bit of DuckDB tricks for high performance on the finding the max patient value, but you could also use kind of a standard SQL window function here. You could run this in a lot of ways. I'm actually just going to run it for the sake of the demo within the Flat Quack command line tool. In the real world, you might want to have this as a DBT model that sits on top of these other two tables, or as I mentioned, do this in Salesforce or some other data tool. So with that, I'm going to try to flip to the demo, and we'll take a look at how some of this works. Hopefully this will work. This is a live demo of some alpha software, so we're definitely taking a risk here. So if we want to look at the source data here, this is a synthetic data set that the Smart Health IT team makes available based on the Cynthia data generation tool. I have a link to it at the end of the presentation, which we'll distribute if you want to pull in this data. It's about split across, it looks like 13 files. And so not a huge data set, not even a mid-sized data set really, but good enough for a demo on my laptop. And then we're going to use the built-in, that's what the @ symbol means here, Parquet template. So we were going to input NDJSON from any NDJSON in this directory. We could also pass in a path for that if we cared. And so it'll find all these observation files and generate a flattened Parquet out of it. And then this -M here tells us we want to do it in preview mode first. So we're going to see the SQL that's being generated before we actually create it or run it. So we could generate some SQL that sits in a directory, which is a great way to pipe it into, for example, a DBT flow, or we can actually run it, which is what we'll be doing. But here we can see the SQL. So it compiles a1c.viewDefinition.json here. It's created a couple SQL macros just to make it a little easier to read and to work around some DuckDB bugs. And I want to highlight a couple things in the generated SQL. I think one of the interesting things here is that it's generating a schema for the NDJSON to read in, but it's only generating the schema for the fields, for the FHIR elements that are used in the view definition. So it's parsing the view definition, overlaying the FHIR structure definition, finding the intersection there, and then creating a schema to just read those values. And this can save a lot of time on the parsing because it doesn't have to read kind of nested elements within an element if it knows that's not part of your schema. So it's just creating kind of an abstracted FHIR observation to start. Here's the wildcard piece I mentioned. It's looking for all observation NDJSON files, no matter what kind of additional naming they have on them, and kind of treating them as one table. And then it's doing some transformations here where this is a very simple one where it's taking kind of the last segment of the subject.reference path in the interest of time, I'm just going to quickly run the patient contact view definition to create a second Parquet file. XLSX. So we'll do that, and let me just flip to the right monitor here, and to make this a little bigger. But you can see we've generated from this kind of raw FHIR data from these 750,000 observations, a set of 11 patients who we want to reach out to, and we have their lab value and the date stamp of that lab value, as well as their phone number and contact information. So I'm going to flip back to the slides here quickly and just wrap up a little bit so we have a couple minutes for questions. I mentioned that, we used one code to find the A1C lab values. In the real world, often you're looking across a whole set of condition codes, and those get grouped into a value set to make them easier to work with. And so I think we can think about how we would use value sets to make it easy for folks to refer to whole sets of codes rather than having to put the codes into their view definitions one by one. I showed the command line tool, but there's no reason that that FlatQuack has to be run that way. It can be also run as code. And so I want to kind of clean up that interface a little bit and make that more usable. And then lastly, People, I think, are rarely going to run view definitions as a single entity. Really, what you'll want to do is work with a set of view definitions and potentially some analytic queries on top of that. And so I think I want to experiment with some of the ways we could do that in FlatQuack. And then I think as a group, we also want to look at ways we can create standards around that for SQL and FHIR so that you can create kind of a whole set of view definitions and queries for a use case and share that between systems so that you don't have to worry about what tech stack it's running on, but the kind of knowledge artifact is separate from running individual implementations. So I've been talking a lot very fast, so sorry for that. But I think we have a couple minutes for questions if folks have any questions.
So if no question, I will ask, how far are you from passing our tests, Sid?
Yeah, so it passes all of the tests except for boundary functions and constants. So I don't know what percentage that is, 95%, something like that. But everything that's been implemented passes the full test suite. But I think and Nikolai, I guess I would add one thing, which is I think there's like a lot of edge cases. And in compiling to SQL, you're kind of potentially hitting some of those edge cases in real world data and real world view definition. So I think this is where I'd love people to try it out with their real world use cases and see where they run into kind of edge cases, things that break, and then we can add those to the test suite for everyone, but also fix those in FlatQuack.
What was the most challenging piece to implement?
That's a really good question. There were a couple challenging things. I think one of the interesting things about a compiled to SQL view runner, and I know you're going to talk a little bit about view runners in a minute, is that some of the tests only fail if it can only be determined at runtime. So if you have an output of a FHIR path expression that only has one value, FHIR path should take that value and just treat it as a scalar rather than a list. But you can't know at kind of compile time whether your list is going to have one value in the end or more than one value, because it depends on the underlying data. So I actually added a little DuckDB function that at runtime will throw a DuckDB error if the value output is supposed to be a scalar and the FHIR path list has more than one item. So there are like some tricky things like that where the spec is, if your view runner is actually running the SQL, it's a little bit, or running the filters and running the transformation, it's a little bit easier than if you're trying to compile it so that it can be run in multiple tools.
Yeah, probably last question. Is there any plans to port it to another SQL engines, not only DuckDB?
That's a really good question. So I tried to isolate all of the DuckDB specific parts in one module. So a lot of it in terms of kind of parsing the view definitions, transforming them, extracting FHIR paths from them, simplifying the abstract syntax tree so that it can easily be transformed into SQL. Like all those pieces are generic. The actual SQL it generates, though, in order to be performant, is very specific to DuckDB. So I use a lot of internal functions that work with lists and structs in order to be able to very quickly do fairly complicated transformations. And I think if you want to be performant on other databases, Nikolai, you can talk more about how this works in Postgres. But I think you kind of have to at least tune that piece of it, that piece of the SQL generation to each database. So the short version is, I think it's certainly possible and possibly even fairly straightforward to port it to other databases, but I would expect the generated SQL to look very different from the DuckDB SQL if you want to be performant on a different database. So also that's an area where if folks are passionate about a different database environment, I'd love to have contributions, because I think I'm going to continue trying to focus on DuckDB since that's what I'm hoping to use for a lot of my work. Happy to merge in pull requests that add support for other database engines as well.